Okay, so now we have seen conceptually how would backtracking look, or what are the steps we need to take care when we are using backtracking algorithm techniques. Next, what could be more best than diving ourselves into one of the real problem and seeing how can we actually use backtracking to resolve the issues or to actually solve that real problem. So the problem that I want to take today at hand, in which we'll be using the backtracking technique, is n queens problem. So let's first define what does this n queen problem mean. So in this problem, we have, as it says, n queens. So we have n queens, and our task at hand is to place them on n into n with a board with n rows and n columns such that they do not attack each other or any queen. Now, what do we mean by do not attack? I assume all of you have played chess some or the other point, or at least you are aware of the basic rules of chess. And this n queen problem is kind of a derivative of some problems that we solve using the chessboard, or some other games that we can play using the chessboard. So what it means is the queen terminology is adopted from the chess. So if you remember how we play chess, chess is nothing but 8 into 8 board, right? And in that, so we have our 1, 2, 3, 4, 5, 6, and one more. Okay, so chess is 8 into 8 board. So our n is nothing but 8 over here, 8 rows and 8 columns. And that's where the problem will then become 8 queens problem. If you are using exact chessboard to play that, we can change any n in actually n queen problem. The queen in chess can have, so the queen of chess can be moved in different ways. So it can move, any queen is one of the most powerful artifact of chess among all different things that we have when we play chess. So the queen can move one step forward, one step backward, one step right, left, or any diagonal, right? Basically anything in its surrounding. So all these are its attack position. It can attack anything that's there along its same column. It can attack anything that's there along its same row. It can attack anything that's there along its same diagonal, both up and down, as well as the anti-diagonal. All this 4 different directions. So anything that's lying in one of these little boxes that are under its path of attack is considered like, actually, so those are the components where you cannot place queen for this problem. So what this exact problem is saying is that given that this 8 into 8 board, now place your 8 queens. So we need to place 8 queens in such a way that they do not, so none of our 8 queens attack each other. And they are perfectly fine in staying in those positions. Now, looking at this, take a minute to think. And what do you think? Do you think there is a solution for this problem, or this is a problem that can never be solved? If you are supposed to manually solve this problem, if you are supposed to come up with such a combination, do you think such a combination would exist? To together find our answer for that, Let's start from a smaller n. So let's have two queens problem first. Let's see if the two queens problem has a solution. So for a two queens problem, we'll have 2 into 2 board, which is something like this. And our problem quest is, the task at hand is to place two queens in this board in such a way that they do not attack. So let's say we put our first queen here. Where can we place our second queen? Here, 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 no, everything is attacked. So no way we can place our second queen. Our second option would be that, let's say we place our first queen here. Where can we place our second queen? Here, here, here. Nope, nothing works. So unfortunately, two queens problem cannot be solved, or the solution doesn't exist. Let's see what happens for three queens problem. So in this case, then you have 3 rows and 3 columns. And now the task at hand is to place 3 queens inside this board such that they do not attack any other queen. So let's say we start with placing our first queen here. The second queen, we can, so definitely why I'm going, so first, if we have one queen in a row, observe that you cannot place any other queen in that row, right? So it's quite logical that rather than trying to see if you can place something over here or something over here, it's quite logical to directly move on to your second row, because anything in the same row or column, you can take, I'm moving here row by row, but you can have a same algorithm or same thought process to move column by column. So here I'm thinking that, okay, no other queen could be placed in this row if my first queen is in that row. So I'm going to the second row and I'm seeing, okay, in this second row, where can I place my second queen? For n queens to be unattacking in this board, you should have at least one queen in each row, right? If you go by row to solve your problem, then that's an observation that in order to fit n queen in your n rows, you should have at least one queen in your each row. So the second row, let's see if we can fit any queen there. We cannot fit here. We cannot fit here because it will be attacked diagonally. But the third queen, yes, we can fit the second queen. We can fit in this third position because it won't be attacked neither by the row, nor by the column, nor by the diagonal. That's good. Now let's see our third queen. Can we come up with some placing solution for our third queen? Here you cannot place, it will be attacked by the first queen. Here you cannot place, it will be attacked by the second queen, diagonal on the bottom end. And here again you cannot place because it will be attacked by the diagonal of the first queen. In the same case, are we done? Are we done exhaustively searching for all possible solution that this three queens problem could have? No, we are not done, because we just started with our first queen's position in our first box over here. But there could be multiple solutions where we can backtrack. So now this is where backtrack human thinking process is coming into this algorithm. So carefully think and analyze your thought process of how you're thinking. So now in this case, we were moving forward. First we put first queen, second queen, and the third queen, we didn't find any solution. So we backtrack. Go to the second row. Is there any position where that second queen could be placed anywhere else apart from where it is currently? Any legal position? No, it doesn't have any legal position, right? So then we backtrack again. And the second time we are backtracking 1, backtracking 2. Now here we are at the first queen. Are there any legal position that the first queen could take and that we have not seen? Yes, there are 2. Either we can place it here or place it here. So now our algorithm should do something like this. So it should place this first queen over here. And now we should see if there is a possible solution. So again, process things in a forward way. So now if the first queen is there, where can we place our second queen? Can we place it here? No, it will be attacked by diagonal. Here, no, it will be attacked by the same column. Here, no, it will be attacked by diagonal. So we cannot place, and that's where, so as our first observation is that for n queens to fit in n row board, there should be at least one queen in every row. If we can't fit a queen over here, then definitely we can never fit two queens in this row, right? So definitely there's no point of checking for the third row. We can, this is the dead end. This is how we realize our dead end for this particular problem from our observation. So then our quite natural third choice, so we backtrack again because we hit a dead end over here, we backtrack again. We see what is our third option. So I would just erase this and I would see our third option over here if we place the queen at the last position. Now, people who are smart might be thinking from the diagonal symmetry or the rotation in this problem, and you would have already thought that, oh, if putting queen in the one in the 0 0 box doesn't work, then putting the same queen, so I'm saying this is 0 comma 0, this is the first row, this is the second, this is the first column, second column, 0 row, first row, second row. So putting the queen in this 0, that's my 0 row, and second column. So putting the queen in 0 comma 2 will, analyzing it from the symmetry and the clockwise and the rotation, we can say that the solution wouldn't exist. But well, those are some of the optimization techniques you can use when you're actually coding for n-queen algorithm. But here, let's say that we don't know any of such optimizations, and we are not that smart to actually analyze those things and then put it into our code. So if we are just going with the brute force way, then we would definitely check this third possible option, the choice that we have, and that's unseen. So if we place a queen there, in the second row, we can place a queen over here. That wouldn't violate any, this queen won't be under attack because it's not attacked by the row, by the column, or by the diagonal of the first queen. So after placing the second queen there, can we place any position the third queen? So we cannot place here, it will be attacked by the second queen. We cannot place here, it will be attacked by the diagonal of the second queen, and we cannot place here because it will be attacked by the column of the first queen. So, well, this kind of, so we are exhaustively, we have analyzed all the, if you are making a similar table like this, so at every stage that we have, in this case, our stage is every row. So for every row, row 1, row 2, row 3, we have exhaustively analyzed all our choices, and we have ensured that when we take these choices, we mark them as seen, and then we are reaching the dead end without finding the actual solution for n queens, for 3 queens problem. So, well, 3 queens also cannot be solved. So now after doing this, 2 queens cannot be solved, 3 queens cannot be solved. Do you think, can we solve n queens where like n is anything greater than 3, where n is 8, so can we solve like 8 queens? Well, I would say that first time when I tried this, then I just gave up because I thought really hard. I thought really hard for maybe 5 or 10 minutes. And then I was like, okay, I don't think solution will exist. So that's, to be true, that's my true first opinion over this problem. When I ran into this problem, like when I was in school, maybe in 4th grade or something. And that's when I was thinking, can this problem be solved? At that time, I was not well versed with algorithms and data structure but I was just trying to solve this algorithm in a normal human way, how we play chess and something like that. So that was something I decided that it cannot be solved. But it happens that you should have more patience to analyze some things than just 5 minutes or 10 minutes, which I realized over time from then. And now, if we take a four queens problem at our hand, we would see that there exists a solution. Indeed, there exist multiple solutions. So our problem statement is as soon as we find the first possible solution, then we exceed. So as soon as we find the first possible locations in which queens can be arranged such that they don't attack each other, four queens don't attack each other on 4 by 4 board, then we will exit the program or return that location of what is the position of queens. Now, as I already mentioned, the diagonal symmetry and the rotation play a factor in this 4 into 4, 4 cross 4 board. So you can just assume that if we have one solution, there is the chance of another solution that falls under the diagonal symmetry or the rotative symmetry of that 4 by 4 board. So, but anyways, we'll be discussing today just to find how do we find that one solution, the first solution, right? So when we have four queens problem at hand, we can do the same. You can do the same example and find the human solution. I'm not going to walk through the example here, as detailed as we saw for two queens and three queens, just in sake of time. And I'm sure you could do that. That's something you are capable of. So let's just see. So we'll take an example of four queen, but our main task here now is to how do we design an algorithm. So let's just see the things that we can do, or what are the different options, or what is the data structure that we would use for this algorithm. What are the steps that we need to be mindful while designing this n queen problem solving algorithm. So the first thing is let's call it n queen. So the first thing, the naive most algorithm. I highly recommend all of you to think of the most naive algorithm when you start working on any new problem. So what is the naive most algorithm that we could come up with to solve this n queens problem? Or what is that straightforward solution, which might not have the good time complexity? It might run for a very long time, but it assures that it solves the problem. And that's the most important thing, to come up with initial, and then slowly you improve things one by one. And then finally you take all those complex cases into account, and then you have this amazing complexities, amazing reduced complexity compared to a naive or a straightforward. Okay, so what is the naive algorithm that we could think of it here? It's pretty straightforward, that generate all possible configurations of queen on board and print a configuration that satisfies the constraints that's given to us. So let's write it down. Generate all possible configurations of queen on board, queens on board, and print a configuration that satisfies the constraints. So here the constraints are that any queen should not attack any other queen. So why not just have like all the possible combinations in which this n queens could be placed on this n into n board exhaustively, like literally all possible n, putting n elements on n into n board, those combinations. And then out of these all combinations, we'll see one by one if we find a configuration in which none of the queen attacks each other, okay, we are solved. We return that particular configuration and we return out of the program. Is this going to solve our n queen problem, having this approach? Is this good, straightforward approach to take to solve this algorithm? Yes, it is. So if we do this, though our algorithm would run for terribly long amount of time, but still it would be able to solve, right? Generating all possible configuration is going to be challenging and time consuming, but we would be able to get answer with this very straightforward solution. Now let's look into thinking of solving this algorithm, particularly by using the backtracking algorithm design technique that we are looking today in our class. So if we want to use backtracking for this n queens problem, then what are the steps we need to take care and how would we logically proceed? This is nothing but I'm going to formalize our thought process that we did when we actually looked into if these two queens and three queens has a solution or not. So the first step is start in the topmost row, placing queen at one of its choices. So we can choose the first choice we want is to place queen in the leftmost corner as we did when we looked at the examples. And one of its choices. The second step, well, when we are designing the backtracking algorithm, what are the two things that we need to remember or that we need to be careful? The base case and how do we reduce the problem into a smaller problem? So how do we chop the problem? How do we progress towards the base case? So the base case, in this case, our base case would be nothing but when we solve the problem, right? When you actually find the configuration where none of the queen attacks each other. So if all queens are placed, return true. This could be our base case. We would be encountering dead ends. So we would be encountering a situation like this where you have no option where to place your queen in that row, and that could be accounted as a dead end. So there are multiple ways of designing a backtracking algorithm where you can have different, depending upon your thought process, you can have different base case and different dead ends. So in this way, for this example, let's assume that this is our base case where if all the queens are placed, we return true, and that's our base case. We get a solution to that algorithm. Now, third, while we are tracking, so now comes the more interesting part where actually the recursion and backtracking would happen in this step. So what we are doing recursively is we want to try all columns in current row. So we started with the topmost queen. We placed that queen. Then we know that only one queen can exist in each row. So we move to the second row. So now second row is our current row, which I'm just calling current here to be more generic. So our second row is the current row. And then we see that, okay, in which column of this, when we are placing our queen in our second row, which column is well fit or well suited for this second queen. Same way, when our current row is the third row, then we would see that, okay, which column is well suited for our third queen to be placed in that third row. So this generically, it's try all the column in the current row to see if the queen can be placed without being attacked by anything that already exists on the board. So in order to do this, we would need to do following. in current row. What are the things that we need to do? First, if the queen can be placed successfully in this column, so let's say we started from the first column or something like that, so that whichever the column at our hand is called this column, then mark this. By this I mean your row comma column for that queen as partial solution. So if you remember, as initial definition of backtracking, first we want to find the partial solution, and then we want to see how our partial solution helps us to explore or make progress towards a complete solution. So if the task at hand is to place the second queen in the second row, if we can find a position that the second queen is not attacked by the first queen, then well, put that queen there and mark that state of the board where first queen and second queen are placed, the rows and the columns of those. So I would let's call it as a state of that our board as our partial solution. And we are not yet done after finding our partial solution. So then our task is, and recursively check if placing queen here leads to a full solution for other rows. So we place that queen there, and then we proceed to the other rows. And we would do the same thing that we did for this row. So that's why the word recursive comes here. So recursively check if our decisions that we have made previously could lead us to a complete solution. And recursively check for complete solution in other rows. So every time we have something that we think is a good position for this queen, but that need not be the good position, right? Because the other queens might, when you proceed to your other rows, then you might encounter that, oh, like you might end up with a dead end, and that's when you have to backtrack. You might, and so in this particular problem, as opposed to what we saw in the maze example, here you might have to backtrack twice, as we did here in the three queens problem, right? We backtracked twice when we placed queen in one of its position. So whenever you place a queen, that's just the partial solution. And then you still need to recursively check if it's valid for other rows. Otherwise, you backtrack. Still, we are not done. We have the second step. If placing queen in any particular row and column leads to dead end. This is what I was talking about. You should always account for dead end when you are logically putting down steps of your algorithm. Dead end, base case, and making progress towards your base case. These are the things that you need to account for. Then mark it C, same as what we did previously when we took the example of maze. We mark it seen. The second thing is we backtrack. Mark it seen, backtrack, and go to, here I would say again, step I, right? Because we are not yet done with, so we backtrack and then we do again for all the columns, the remaining unseen choices of that row. So we go back to I to try other choices. And once we have backtracked all the way until our first row, And then we realize that, okay, there is no possible other choices left unseen. That's when we say that, oh, solution doesn't exist. What we did for 2 queens and 3 queens. But for all the problems that are greater than 3 queens or 4 queens, 5 queens, a solution exists. At least that's established right now. So we can be confident that, okay, our algorithm will run, and then it will give some end as a solution if we have coded it right. So that's it. Then these are our logical steps that we would think that, okay, these are the things that we need to take care. So once you have these kind of logical steps accounted for in your thought process or on your paper or on your computer or something, then next part will be to actually write an algorithm. Now, first thing, as soon as we start writing any algorithm, what is it for any problem, in order to solve any problem, as soon as you start writing any algorithm, what's the first thing you need to think of? Data structure. So what's the data structure that you want to use for this algorithm? What is the data structure that you think would be a good fit to use for this algorithm? I know there are some thoughts popping in your mind. Metrics. Metrics could be the straightforward data structure, because we are using a board. So the choice of data structure is pretty broad. And one of the most straightforward data structure here we could opt for is metrics. Or maybe a metrics could also be called as 2D array, right? Two-dimensional array. There are also other data structures that we can actually use that include, so if your answers in your mind were stacked, you are correct. You can use stack to code this algorithm. If your answer was just one-dimensional array, well, I would say you are well ahead of thinking of how to optimize this algorithm already. So considering some of the observations more in detail, we could reduce this problem to use just one-dimensional array rather than using two-dimensional array. I would leave the task of how we would code using the other data structures up to your end to think of, and how would you actually utilize these other data structures to code. But first we would see the straightforward option over here, which is by using a two-dimensional array or by using a matrix. How would we code for n-queens problem? So now if we are diving into writing a code, please don't go by the exact syntax that I'm using to write when I explain, because it's just for the algorithm purpose. So if you exactly type what I'm writing into your console and execute that, compile that, I'm sure that it wouldn't compile. So it's not to go for the syntax, but it's more to go for the logic of the algorithm itself. And once you know that, syntax is always at just one Google search away. So you can always do that. Okay, now that being said, let's start. So first thing I like to start with in any code I write is with the main function. So int main. Here I am having this board NQ, and I want to solve the n-queens problem, which I'll call in short as NQ. Let's just have that function solve NQ, call that function. And what else? Do we have to do anything else in the main function? No, pretty much that's it. Return 0. So if NQ function doesn't return anything, I hope it does. But if in case where solution doesn't exist, like if n is smaller than or equal to 3, we definitely don't consider the n should be positive in this case, n cannot be negative. So that's one of the assumptions for this problem itself. So if we don't find, then we return 0, and that's it. So this would be our cute little main function. So next, what do we want? So definitely we want to then define this function that we called solve NQ. What would solve NQ return? Something maybe like a bool, maybe just a true if we can solve this NQ problems or a false. It could actually return the position of the queens in that, but let's assume that we want our answer in terms of if we can solve this or not. So let's assume that we just want to return both. So it's true or false, and we have solve NQ function. Now, inside this is where we would need to dive in more further and see what are define our data structure of the board itself, right? Because this is the place where we would see if the board, like initialize the board. So let me do that. Int board. As we just discussed, we want to use this two-dimensional array as our base data structure. So the board will be of n into n, where again, you would take n as an input, either as an executable argument, or you might be solving like 8 queens problem or 4 queens problem with particular n. So there your n would be then 8 into 8 or something like that. So please consider that we add those things into our program. So here our board will be nothing but it will how we actually define or initialize the board is with 0 elements. You can initialize it with 0 or with -1 or anything. But whatever you're initializing it with, that technically means that at that position, the queen doesn't exist. So whenever we are placing a queen anywhere, we'll change that 0 to 1. And 1 means the queen exists at that position. When we write our programs, we need to think into binary. And in this case, the binary is queen exists or doesn't exist. So 0 or 1. That's what I like. You can use -1 and 1. You can use anything you like. So if we have 4 queens problem, if we have 4 queens problem, then we have our board something like this. And then we have, I would like to call this other function. I'll just go to the next whiteboard. I'll call this another function if solve NQ U2. So now this function is going to take the board as input, the board that we just defined, and it's going to take our first row or column that as input. If we are processing, if you want to write an algorithm, which I'm writing here, considering we proceed row wise, then we take 0. If this is equal to false, so we did everything, we backtracked, and finally for this board, for the particular board, we were not able to come up with any solution. So 0 is the solution. And if that happens, then cout, no solution. So it depends on how you are incrementing this variable. For like, because I have false over here, I would like to assume that, okay, if this condition is true, then the solution exists. If this function returns false, so this is the row that we started with, this is our board. If it returns false, then the solution doesn't exist. So we just will print out or cout that no solution. Otherwise, we want to print solution. Oh, I remembered this function returns bool, right? Remember that this function that we are writing returns bool. So we cannot return our solution to this. We can return just true or false, but we can definitely print our solution within this function. So let's do that. It's totally optional if we want to, if the problem requires us to print, but we will just have another function called print solution in that case. So we print solution. In order to print the solution, this function should take as an input argument our board, because it's going to print a particular state of that board, which is a solution. So it's going to take our board as input, and then that's it. So return true, because our function is bool, as we remember. So we need to return true or false. So if we are able to print the solution, we return true. If we are having no solution, then we see out that there is no solution, and we can return false over here. So we can have an additional statement to return false. But these are our integrate details. Doesn't hurt, you can assume, and then you can work through it. So now in this function solve, we solve NQ. We then use two other functions, right? One is solve NQ util, where we pass the board and we pass the row that we are working with. So inside this function, now we want to do all the operations that we are doing with a single row. And then we use this another function, print solve. So definitely we need to write these two functions next. Let's write this function bool solve NQ util. Now, as this function, when it called, you see that it's taking input as int board, right? The first argument that it takes as input is board. And your n into n, again, n could be 4 for our 4 queens problem. And then it takes another input as your row ID, which we passed as 0 over here. So we start with the topmost row. So what do we do inside this function? We start with if row is greater than equal to n. Come on, we need to find. So first thing in any function I write, if that function is having any loop or any recursive calls, then the first thing we want to think is, okay, how would we exceed that? So now this is the task that we are going to do with all the rows. So definitely that gives you an intuition that you can use recursion over here, because it's the same task that you do for first row that you might have to do for second row, third row, fourth row, and so on. And as soon as you think in the direction that you want to use recursion, then you have to think, okay, how would you exit this recursion? And in order to exit this recursion, you will need the base case. So here our base case is if the row is greater than equal to n. So as soon as n is our maximum size of the board, so that's 4 in this case. So if as soon as our row ID becomes greater than equal to that, we don't have to proceed anything further. Like that's the last step that we execute. So if our row is greater than equal to n, then we just return true. So this is our base case in this algorithm. Now proceeding further, we would then have a for loop where we do int I is equal to 0, I less than n. See that here we have less than equal to, because we are starting our index from 0. So as soon as it becomes 0 to n minus 1, that means we covered n rows, and that's what we want to do. So as soon as it becomes n, that means we are kind of overflowing from our board. So that's where we use there equal to, and because we are starting our iteration from 0. And then we have this I plus plus. What do we do inside each of this loop is if I am calling this one more function is safe, which would be responsible to find if that position is safe for this queen to be placed. We will define the function soon. So if is safe, and in order to say that if this position is safe, this function needs to take board, it needs to take a row, it needs to take the I, which is the column index. Because as you see, when we were checking for, when we were manually proceeding for this algorithm over here, okay, I need to be slow and patient in order to move these things, otherwise they come back. I'm sorry. Okay, there we go. Slow and steady. Okay, okay. So when we were trying to place our queens manually in this board for each row, we went one by one exhaustively through all possible places where we can place this queen across its column, right? When we are proceeding from here to here, we are changing the column of that. So that's exactly what we are going to do in this algorithm. So I think I'm getting hang of it. Oops, I jinxed it. Okay, there, yes, there we go, finally. So then we have this function. So I represents that boxes, like that column ID over here. And inside this is safe function. Once we call this function, if this is true, if is safe, board, row, and I. So if it returns true, if placing a queen there is safe, then board, row, and I'm just accessing that particular matrix of that particular element in our matrix that we defined over here, right? I'm accessing that particular of that row and of that particular I. Let's assume it's this, so then it will be this element over here. That is equal to 1. As I said, if placing queen is safe there, we place the queen there. And we use bit 1 to say that the queen is there at that location. If solve NQ util board, comma, row plus 1. So now people who are active and with me until this step, they would have made it out that this is our recursive step, right? Because we are again calling this solve NQ function inside itself. But definitely, as we need to make progress towards our base case, so our arguments are different. Board will still remain board, but our argument is row plus 1. And our base case is when row is greater than equal to n. So adding something is making progress towards our base case in this example. So this is the recursive step that we do. And if we get through the recursion, then finally, so we again imagine things as those boxes that we discussed in class. So we are calling recursive function and then we are computing when we exit each of that. So what we return is true. That will allow us to exit the board. And then we got to backtrack, right? So we backtrack where we have our board, row, and I is equal to 0. We backtrack, we find out we are at the location where our board row and I is equal. So no, if we hit a dead end. So when we are doing this is our recursive step. If we hit a dead end, recursive step, if we hit a dead end while doing this recursive step, then we have to backtrack. And when we are backtracking, remember that we marked board as 1. So while we are backtracking, we need to assume that we remove the queen that we originally placed there, right? We again need to make this 1 into 0. And that's what we are doing here. Something that we did here. Then we recursively went inside this loop. If we hit the dead end, that means if we didn't find the solution, then we come back, we backtrack, and then again we change this bit originally that we set as 1 because we placed the queen there. Now we set that as 0 because now we are backtracking and we are removing our queen from there. So this is our backtrack. And that's it. So we are done with the backtrack. We'll close our if loop, or I open my if loop over here, and then we'll close our for loop. So this is our solve enqueue function, which is a recursive in nature, where we are visiting each row one by one, and then we are seeing all possible columns in which we can place the queen in that row. And we are doing it recursively until our rows of the board are over. And if we hit a dead end, we are going back, backtracking. We are removing the queen that we already placed. When we backtrack, we are exploiting other choices that we have in the original row. And then we are doing it again and again until we see that, until we encounter a solution. So I would say this was one of the most complex function. The another a bit complex function is the is safe, right? Remember we called here is safe, which is yet to be defined. So now let's define is safe. Is safe is basically checking for all the attack. If we place queen over here, then is it safe to place the queen over here? Or if we place it, will it be attacked? That's what we want to do. So again, this function would return bool is safe. What the arguments we passed for this is obviously the board, the row, and the column, right? So the board, which is board and like the matrix of the board, int row, that's our row ID, int column, that's our column ID. Definitely row and columns are int because they cannot be floating points. It's a single row, so it's row 1, row 2, row 3. Then we have, let's have some variables that we need for the loop in this. Well, when I'm actually writing the function, sometimes I put some variables, then I delete them because I don't end up using it in the function. So I'm just having these variables over here from the thought process of how I'm designing to write this function. I'm going to have 2 for loops and then a loop inside. So 1 for loop iterating over the row and something to iterate over column. And that's the reason I put I and j as 2 variables that I would need. Let's see if we would need both of those. So the first loop for I equals to 0, I less than row, I plus plus, if board. So here too, there are 3 things to check for, right? We are checking it if placing queen over here is attacked by any other queen in that same row, any other queen in that same column, and any other queen in that same diagonal. So three things that we need to check here. So we'll have like a concept of 3 loops, and each loop checks if there is any other queen. So in order for us to safely place a queen at any location, there should be no other queen in that row, there should be no other queen in that column, and there should be no other queen in its both the diagonals, diagonal and the anti-diagonal both. So we will, that's what our loops will do. So that's what I'm doing here. So for checking if there is no other queen in that row, so I'm keeping the column ID constant. I'm keeping the column constant, and I'm changing over different rows. So we are moving in a vertical direction where the column ID is same, but we are changing our row ID. So I is a row ID over here. If I don't have to write if this is equals to 1 because it checks for 1, or that's what I'm assuming that it's checked. So it's just for your clarification, I said it. So if this is equal, if the board I and column has any 1, so that means then that will have, that means that it has a queen, then we return false. And this return false is returning from the is safe function outside, right? So because if there is another queen that exists on the same row, then there is no point of computing. So in this case, if there is another queen that exists in the same column, this is what we checked for the column, because we changed over the row ID and we kept our column constant. So if there is another queen in that same column, then we return false. Now it should be quite obvious that we are going to do the same thing. Well, I'm thinking I can use I again. So maybe I might have to erase that J later. But then, yeah, here definitely I can use I again. So if I is equal to 0, if I less than column, then do we have to check? Because this is the function that we are calling within each row, right? Here already. So, okay, because we are calling it just for one row, we don't have to check for all the rows. I hope you get this observation, right? So I was about to write a loop for the iterating over different rows. So something very similar to what we did here, having arguments of row comma I. But then I just realized that there's only one place we are calling this function from, is this. And this has just a single row ID. So we are not changing that. So we don't have to go and iterate and check for all the rows. Okay, that saves our task. So then we will check for diagonal and the anti-diagonal, both of them. So in order to check for the diagonal, we have if I is equal to row, in this condition would be a bit different from the above one. If I is equal to row, j is equal to column, and if we have j is greater than equal to 0 and j is greater than I is greater than equal to 0 and j is greater than equal to 0, then we are reducing the i's index and we are reducing the j's index, right? So this both is the declaration, this will be just the comma. So we are initializing I is equal to row, j is equal to column, and then we are reducing the i's index, we are reducing the j's index. This is the best part about a square. So what I just did in this loop is that, let's say if we are finding if this element, if placing a queen over here is safe, then if I want to walk over the diagonal of over this diagonal of this box over here is that, of this element over here is that, then I will just reduce the I index and j index by 1, right? If this was 2 comma 2, then this is 1 comma 1, this is 0 comma 0, right? So that's exactly what I'm doing here. I'm walking through until it's greater than 0 and I'm reducing its index. And then inside it, we are checking again the same thing as we checked. So if board of I, j, because here we are using two variables, return false. It's exactly what we did above, right? The same steps. So I don't need to explain them again. And now there is another for loop that we need to account here for, is to check elements in the other anti-diagonal. So because, okay, so one is checking this side. Now we are filling elements row by row. So first we fill this, we fill this, we fill this. So while we are filling this row, we don't have to account for anything that's going to be below that, right? That should be clear because that is empty and that's not going to violate our constraints in any way because it's empty. The only chances of queens being placed is above whatever row we are wondering if we can place this element or not. So we don't have to deal with anything to do with anything that's below of the row that we are handling at hand. We only need to worry about above. Now above, one is the diagonal and the other is anti-diagonal. So in order to like find out the index of anti-diagonal. Now what we would do is we would increase the column ID, right? Because from this, now if this was 2 comma 2, this is 3. So the column ID is increased 1, 2, and 3. And maybe later it could become 4. Okay. So 1, 2, 3, 4. So the column ID is increased, but the row ID is still reduced. So if this was row 3, row 2, row 3, 2, 1. Okay, so row ID is reduced. So that's what we want to do in this last loop. Let's write that out. So for I is equal to row, same as before. J is equal to column. I greater than equal to 0 and j less than n, because this column, the last column that we would have is n minus 1. So if j until j is less than n, we are good. We don't want it to be less than equal to n, because that will be, because we are starting our index from 0. That's why we have less than n rather than less than equal to. And then we are reducing I. As we saw here, we want to reduce I because we want to go up. But for the anti-diagonal, we will be increasing our j. So reduce I and increase j. Okay, everyone with me over here? We are almost there until the end. So we reduced I, we increased j, and inside that, again, the same things as we perform for these both for loops. So that should be pretty straightforward. Now to you, what we are checking here, if board I, j, then return false. Okay, so these are the things, and that's it. So then once we are done with all this for loops, we want to return. So because we are returning false inside it, if we encounter a dead end, if we are done with all these for loops and if we don't encounter any ones for this if conditions for all these 3 for loops where we checked for the element across the column, the element across the diagonal, and the other diagonal, then we would return 1. So okay, for this row, then for the row at hand, which is in this function solve and queutil, we are considering each row at hand. So for this particular row, which with the argument that we are passing from this function, for this particular row, that it's safe to place queen there, and that's what it would, this return 1 would return. Okay, so then looks like we are almost done. Let's see if there's any other function that's left. Is safe is solved. What's the function that's left? Oh yeah, print solve, print the solution. That function we have not yet written. So print solution. Okay, there we go. Print solution, it doesn't need to return anything, right? Because it's just printing. So white, no more blue. Print solve. And definitely, because we are printing the board, it needs to take the board of n comma n arguments, right? The board size. So this should be, as if you would, as many of you would have already thought, this should be the nested for loop, right? Because you're printing the elements of the board. And this is one of the most straightforward function apart from the main function in this whole program. So int I, definitely define your I and j is on the top. Okay, so I equals to 0, I less than n, because we are starting from 0, I plus plus. For int j, you can define in the for loop or you can define at the top. Int j, j is less than n again, j plus plus, it's nested, so it's inside that. And what we are doing is see out, and we want to see out the board with I and j as its index. So basically it will see out all the elements of the board. And you can have a new line character after the first for loop if you want to print things in this fashion rather than all in a single line. So something like that, and that's it. So that will print our solution, that will print our board with the solution. So this is our program for solving n queens problem, and this will work for any n, doesn't matter, 4, 5, 8, 10, anything. So what I want you to do is now that we have seen the elaborated expansion and explanation of the whole program, I want you to think if we can code, how would you code for the same to solve same problem, same n queen problem using stacks, using one-dimensional array, these two things. And then I want you to compare the big O complexity. Okay, I'm just writing it. So then I want you to compare the big O complexity for each of these, this, and this. If we use different data structures, it's going to be very interesting because with different data structures, you can have different complexity of the algorithm, and that's one of the way how you optimize the runtime of any algorithm by choosing a better data structure. So that's it. Then see you in the next class. Bye bye. If you have any questions, feel free to email them to me.